Welcome to the RBFS Fundamentals Training Series. In this video, we will cover Part 1 of Subscriber Management Theory in Configuration, focusing on PPPoE. In subsequent parts, we'll explore the IPoE and L2TP protocols. The configuration examples and demos in this clip are based on RBFS version 24.9.1. Before we dive into the basics of the PPPoE protocol and its implementation in RBFS, a brief disclaimer: this clip is free to use for non-commercial purposes and is designed to help you become familiar with RBFS through self-study. However, please note that it does not cover all configuration options available in RBFS, and implementation may change in future versions. Here's an overview of what we'll cover in this video. First, we'll provide a brief introduction to broadband access networks to clarify some key terms. Then, we'll take a closer look at how PPPoE works, explaining the steps to establish, manage, and tear down a PPPoE session. Afterward, we'll put the theory into practice, guiding you through the necessary steps to implement PPPoE subscriber management in RBFS, covering both IPv4 and IPv6 configurations. We will then present some useful commands to monitor PPPoE subscriber activities, which will also help us troubleshooting. Finally, we'll dive into Radius services and explain how Radius can simplify subscriber management. We'll cover both the theory and practical implementation of Radius. Let's jump into a brief overview of subscriber management. A broadband access network is used to connect customer locations, either business or residential, to a service provider. We will follow the terminology used in TR 101, as defined by the Broadband Forum, which describes Ethernet-centric broadband access. At the customer location, the customer premise equipment, CPE, terminates the local loop, providing the interface between the customer's devices and the network. The CPE is sometimes called a routing gateway or home gateway, but for this presentation, we will stick to CPE. Depending on the access technology on the local loop, the CPE can be physically connected to a variety of different devices. With fiber to the home, fiber cables are installed all the way to the customer premise. The fiber is attached to an optical network termination device, which is responsible for translating optical into electrical signals and is connected to the CPE. The remote end of the fiber is connected to the optical line termination device, which aggregates multiple users. Fiber to the building access is very similar to fiber to the home, but instead of a separate fiber to each apartment, there is a single fiber to the building terminating at an distribution point unit. Standard copper cables are then used to connect the DPU with the CPEs. If a flavor of digital subscriber line, XDSL, is implemented, the CPE usually has a DSL modem integrated and is physically connected to a multi-service access node, MSAN, which aggregates multiple subscribers. In the past, this system was called a DSL access multiplexer, DSLAM. The fiber to the curb approach is similar to the XDSL. The main difference is that the MSANs are smaller and located closer to the customer. In case of cable access, the CPE has a built-in cable modem which is connected to a cable modem termination system, CMTS, using coaxial cables. Again, the CMTS aggregates multiple subscribers. The aggregation devices, for example OLT or MSAN, are connected to the Ethernet aggregation network, which then connects to the broadband network gateway. Our main focus in this presentation will be the Broadband Network Gateway, short BNG. Historically, the BNG was known as a Broadband Remote Access Server or BRAS, but we will use the term BNG throughout this presentation. At the BNG, customers typically refer to subscribers or users. The BNG acts as a router that forwards packets between the core network and the customer location providing internet access. To interconnect with the core network, the BNG must support IP routing protocols such as BGP, OSPF, or ISAS. The BNG typically supports MPLS to provide services like Layer 2 and Layer 3 VPNs, along with traffic engineering and fast reroute capabilities. If services such as IPTV are offered, protocols for IP multicast group management and traffic replication may be implemented. While traditional routers focus on these routing features, the BNG also handles key functions necessary for managing broadband users. Most importantly, the BNG is responsible for managing subscriber sessions, which includes user authentication, session establishment, and session termination. One aspect of session management is session accounting to create billing information. In this context, a subscriber session can either be a PPPoE or an IPE session. In this presentation we will focus on PPPoE. Once the session is successfully established, the BNG assigns IP addresses to customers, enabling internet connectivity. IP addresses can be allocated from locally defined pools, DHCP servers, or radius servers. Traffic management includes functions like quality of service to prioritize certain types of traffic, ensuring optimal user experience for applications like video streaming or gaming. It also includes traffic rate limiting. The BNG also plays an important role in applying security policies to protect the network. The BNG is a critical component in broadband access networks, particularly because it needs to support large-scale deployments, with thousands or even tens of thousands of users. As such, scalability and reliability are essential to ensure that the network can handle the high volume of concurrent connections and traffic. Independent of the access technology, an important aspect of the network design is the logical structure of the Ethernet aggregation network. Basically, there are two different VLAN models that can be used: the one-to-one VLAN model and the N-to-one VLAN model. In the one-to-one VLAN model, each subscriber is assigned a unique customer VLAN, or CVLAN, which carries all the traffic for this customer. This provides a direct one-to-one mapping between VLANs and subscribers. New services can be added easily without affecting others. The one-to-one model is recommended because it is simple and offers flexibility for features like backhauling, bitstream access, and QoS. The VLAN ID is a 12-bit unsigned integer, which limits the number of VLANs and thus the number of customers to 4096. In order to increase the scaling, double-stacked VLANs can be introduced. In most cases, the outer VLAN represents the aggregation device. The shared N-to-one VLAN model offers many-to-one subscriber-to-service connectivity, where multiple subscribers share a single service VLAN, or SVLAN. Usually, there are separate SVLANs for internet connectivity, IP telephony and IPTV. Access protocols can provide features such as automatic IP addressing, and enable a framework for authentication and accounting. There are two common access protocols in use: PPP over Ethernet, and IP over Ethernet. IPoE is covered in another clip. In this section, we will explain how exactly PPPoE works. Point-to-point protocol, PPP, is a connection-oriented data link layer protocol. From a subscriber's perspective, it indicates whether the connection to the service provider is active and functioning. PPP has two key components: the Link Control Protocol, LCP, and a set of network control protocols. The LCP is responsible for establishing, maintaining, configuring, and terminating the PPP session. The two ends of the connection are aware of each other's state, ensuring they both know whether the link is operational. The presence of data transmission indicates that the link is up. During periods of inactivity, LCP echo request and reply packets serve as a link checking mechanism to confirm that the remote peer is still reachable. Additionally, PPP supports optional authentication methods to enhance security. A single PPP session can support multiple network control protocols, one for each layer 3 protocol. For example, the IP Control Protocol, IPCP, is used for IP version 4, and the IPv6 Control Protocol, IPv6CP, is used for IP version 6. PPP over Ethernet, PPPoE, is a client-server protocol that encapsulates point-to-point protocol frames inside Ethernet frames, providing the same benefits as PPP while enabling connectivity over Ethernet networks. PPPoE is commonly used by service providers to deliver broadband access, typically over technologies such as XDSL or FTTX. PPPoE communication occurs in two stages, the PPPoE discovery stage and the PPP session stage. In the Ethernet header, the ether type field is set to 0x8863 for the discovery stage and 0x8864 for the PPP session stage. The PPPoE header includes a code field that indicates the type of PPPoE packet, along with a 16-bit session ID field. During the PPP session stage, the PPP header that follows the PPPoE header primarily contains a protocol field, which specifies whether the packet is an LCP, IPCP, or IP data packet. Let's take a closer look at the PPPoE discovery stage. During the PPPoE discovery stage, the PPPoE client establishes a communication channel with an access concentrator, which in our case is the BNG. The PPPoE client is a software component that resides within modern CPE devices. The discovery process involves 4 steps in which specific packet types are exchanged. The PPPoE client initiates communication by transmitting a PPPoE Active Discovery Initiation Packet, PADI. The session ID is set to 0, and the requested service is specified using the service name TLV. If the service name is empty, any service is accepted. The PADI packet is sent to the Layer 2 broadcast address, and if multiple BNGs are connected to the Ethernet aggregation network, they will all receive the PADI packet. When a BNG receives the PADI packet with a service request, it responds by sending an active discovery offer, PADO, packet to the PPPoE client's MAC unicast address. The PADO packet contains a session ID, set to 0, the access concentrator name, and one or more service names indicating the details of the offered services. Note that RBFS does not support the configuration of service names at this point. As a result, the service name is simply copied to the response packet. If no service name is present, RBFS will include a default service name called access. The BNG may also generate a unique AC cookie based on the client's MAC address and attach it to the PADO packet to protect against denial of service attacks. This AC cookie is used unmodified in all subsequent PPPoE packets. Since the PADI was a broadcast message, the client may receive multiple PADO packets. It inspects the packets and selects one based on the service name or other offered services. The client then sends an PPPoE Active Discovery Request, PADR, to the chosen BNG to accept the service. The session ID remains set to 0. Upon receiving the PADR, the BNG generates a unique session ID for the PPPoE session and sends an Active Discovery Session Confirmation, PADS, to confirm the connection and provide the session ID. Once the PPPoE session is established, the PPP session stage begins, and data is sent using PPP encapsulation. The session ID will remain unchanged for the duration of that session. Ethernet packets are now sent unicast. At any point during the session, either side can send a PPPoE Active Discovery Termination, PADT, packet to terminate the session. When a PADT is received, no further PPP traffic is allowed for that session. Once the PPPoE session is established, PPP data is transmitted in the same manner as in any other PPP encapsulation. All Ethernet packets are unicast. The ether type field is set to 0x8864, and the PPPoE code is set to 0x00. The session ID remains constant throughout the PPPoE session. The PPPoE payload contains a PPP frame, which includes a PPP protocol field that indicates the nature of the data within the packet. The initial packets exchanged are Link Control Protocol, LCP, packets, identified by the protocol field 0xC021 in the PPP header. LCP is responsible for establishing bidirectional communication between the two peers. A series of LCP configure request and LCP configure acknowledge packets are exchanged, carrying configuration options such as the maximum receive unit, MRU, magic number, and authentication type. In theory, PPP authentication is optional. However, the RBFS implementation requires authentication to be configured and occurs shortly after the link is established. Valid authentication methods are Password Authentication Protocol, PAP, or Challenge Handshake Authentication Protocol, CHAP. For instance, a PAP authentication request contains a username and password in clear text. If the remote peer recognizes this combination, it will respond with a PAP authentication acknowledge. After the Layer 2 phases are completed, each Layer 3 protocol runs its own network control protocol to exchange configuration options between the peers. For IPv4, the corresponding network control protocol is the IP Control Protocol, IPCP, which handles configuration options such as IPv4 addresses, subnet masks, and DNS servers. For IPv6, the network control protocol is called IPv6 Control Protocol, IPv6CP. IPv6CP works a little different than IPCP. The only option defined is the interface identifier, which is a 64-bit extended unique identifier that is used by router advertisement and DHCPv6 for exchange of configuration options such as IPv6 addresses, network masks, or DNS servers. After a network control protocol reaches an open state, PPP can carry traffic for the associated Layer 3 protocol. It is important to note that multiple network control protocols can run concurrently, and any one of it can open or close independently of the underlying LCP state. PPP sessions can be terminated at any time by sending an LCP termination request from either side. No further packets are transmitted after the PPP session is terminated except an LCP termination acknowledge. If possible, network control protocols should move to closed state prior to the LCP termination request. Now that we are familiar with PPPoE and PPP sessions, let's move to the implementation in RBFS and see how to configure it. Rtbrick's modular and scalable subscriber management, referred to as next-generation access infrastructure, supports a range of access protocols including PPPoE in Radius. This system is designed to deliver carrier-grade Internet access services, with a focus on scalability, interoperability, and robustness. By providing support for multiple access protocols, RBFS ensures flexibility in deployment and compatibility with various network configurations, which is crucial for operators looking to provide consistent and high-quality services to their customers. Rtbrick's implementation utilizes a distributed architecture to enhance both scalability and stability. The distributed nature of this architecture allows multiple processes to manage different aspects of subscriber connections concurrently, reducing bottlenecks and ensuring that the system can handle a large number of subscribers efficiently. There are four main daemons in the Rtbrick distributed access architecture. The subscriber daemon serves as the central component, managing the current subscriber state and handling authentication, authorization, and accounting. It also serves as the interface to the forwarding infrastructure, responsible to request per subscriber QoS, filters, and more. The PPPoE daemon handles PPPoE and PPP sessions for subscribers including subprotocols as ICMPv6 and DHCPv6 where the implementation for PPPoE differs compared to IPE. The L2TP daemon is responsible to manage L2TPv2 tunnels and sessions. The IPE daemon handles protocols related to IPE subscribers like DHCPv4 and DHCPv6. RBFS subscriber management configuration involves setting up various profiles and parameters that control how subscribers interact with network services. This includes authentication, service access, protocol handling, and other functions organized under a structured configuration hierarchy. There are three mandatory configuration options in RBFS. The AAA profile ensures that all subscribers are authenticated before accessing services, authorized to use those services, and accounted for billing and monitoring purposes. The access profile defines various parameters to control how RBFS handles network traffic and client interactions. For PPPoE, the configuration includes various PPP parameters such as LCP, IPCP, and IPv6CP, as well as authentication protocol and other address family-related settings. Finally, the access interface configuration is the anchor point for almost all further access configurations. The interface configuration defines the physical interface name along with VLAN ranges, as well as the access type, which in our case is PPPoE. In addition, the mandatory access profile and the AAA profile are associated with the access interface. Although IP address pool configuration is not mandatory, in absence of other IP address assignment methods, it is a common configuration step. The address pool is linked to the access profile. Keep in mind that all subscriber management configurations and profiles are managed under the top-level hierarchy access. This hierarchy acts as the central point for defining and managing all access-related settings. Enough of theory, let's put this into practice with a simple example. We begin with the access profile configuration. This is done via the set access profile command. We need to define a profile name. In this example, the profile name is PPPoE_access. As all commands in the RBFS configuration use small letters, I personally prefer to use capital letters for profile names, but you can use any other naming convention. In this access profile, we define the routing instance to be the default instance. Next, we enable the PPPoE protocol. The PPP protocol configuration consists of the LCP configuration and the network control protocol configuration. LCP configuration offers a range of parameters that can be tuned. We leave all of these at the default values and only set authentication to use PAP or CHAP. And we set the network control protocol to IPCP and define the loopback interface as the source interface for this communication. Finally, we enable the IPv4 address family. Going back to our PPPoE configuration building blocks, we have now completed the access profile configuration. Let's move on to the AAA profile configuration. AAA is short for Authentication, Authorization, and Accounting. The AAA profile is a mandatory configuration that serves as a cornerstone for managing and tracking subscriber activities. The AAA profile is configured using the set access AAA profile CLI command. We need to define a profile name and an authentication method. RBFS offers a couple of options for authentication. With the local option, the subscribers are authenticated based on locally defined user profiles. The radius option is used to send authentication requests to a radius server. We will come back to this option later in the presentation. For the sake of simplicity, we accept all user credentials by setting the authentication method to none. After completing 2 out of 3 configuration tasks so far, we proceed to configure the access interface. So, let's move on to the access interface configuration. We use the set access interface command hierarchy to define the access interface. Using the question mark again, we see that we now have 3 options: untagged, single-tagged, and double-tagged. In our example, we choose double-tagged, which is the most common one for the one-to-one VLAN model discussed early in this clip. The physical interface, to which our clients are connected to, is hosted 004 and the VLAN range is from 128 to 159 for the outer VLAN, and 101 to 200 for the inner VLAN. The access interface configuration provides some optional settings, for example the maximum number of subscribers per VLAN. We will limit ourselves to the mandatory tasks. We define the access type as PPPoE. And we associate the PPPoE_access profile and the PPPoE_AUTH, which we have previously defined, with it. Once this is done, we commit the configuration. Now, we switch to a server connected via interface hosted 004 to the RBFS system. This server has an application installed called BNG Blaster. The BNG Blaster is an open-source network tester for routing and access protocols actively maintained and evolved by Rtbrick. For more information about the BNG Blaster, visit the project documentation on GitHub. We will use the BNG Blaster to generate a PPPoE client session. So, let's start it with a predefined configuration file for an IPv4 single-stack subscriber. As we can see, the PPPoE session fails to establish. This is a good starting point for some initial troubleshooting. Switching back to RBFS, let's monitor the subscriber login attempts. We can see that the subscriber periodically tries to connect, but the session is terminated immediately. A very nice feature in RBFS is the Show Subscriber History command, which displays previous logins, successful ones as well as failed ones. We spot that the termination reason is no IP address. The client does not have an IP address, nor does it get one assigned from the BNG. As mentioned earlier, the address pool configuration is not mandatory, but as we do not have defined any other method to assign an IP address to the subscriber, we will fix this issue by creating an IPv4 address pool. An IPv4 address pool is defined using the setAccessPool command hierarchy. In our example, the pool name is defined as PPPoE_pool_IPv4. The command requires to configure the first and the last IPv4 address in the pool. After we have created a pool, we need to assign this pool to the access profile. And while we are at it, let's add a primary and secondary DNS server to the access profile as well. For the client to get internet connectivity, the subscriber IP address needs to be routed to the core network. For stability reason, it is not a good idea to redistribute the assigned IP address one by one into any kind of routing protocol. It's best practice to define a static route for the complete address pool with nexthop set to null. So, we define the nexthop profile first and the static route afterwards. As we are running BGP in the core network, we will redistribute this static route into BGP. After committing this fix, we can restart the BNG Blaster and see what happens. Let's recap the configuration we've created so far. I will go over the steps briefly. Please pause the video at any point if you need more time. For a minimal PPPoE configuration, we must first create an IPv4 address pool as there is no other method to allocate subscriber IPv4 addresses. Secondly, we create an access profile in which PPPoE and PPP parameters are defined, and the IPv4 address family is activated and a previously defined address pool is referenced. DNS servers may be defined here. Thirdly, an AAA profile must be created that, in the simplest case, accepts all subscribers without any further inspection. Finally, an access interface is configured on the corresponding physical interface with the associated VLAN range. The access protocol is set to PPPoE and both, the access profile and the AAA profile are bound to it. Looking at the configuration in JSON format allows us to better understand the dependencies between the individual building blocks. So far, we have successfully configured PPPoE sessions to support IPv4. The process of configuring IPv6 support is similar to that of IPv4, but there are some key differences. Instead of using IPCP, the IPv6 control protocol, IPv6CP, is used as the network control protocol for IPv6. The assignment of the IPv6 address to the subscriber's CPE device on the WAN link is handled through IPv6 router advertisement, which is part of the IPv6 neighbor discovery protocol. Router advertisements can provide a variety of network parameters to devices supporting IPv6 within the network. The most common prefix length for an assigned network is /64. Although this may seem like a large address space, it is necessary for several reasons, including stateless address auto-configuration and other features of the neighbor discovery protocol. As a result, a /64 prefix is recommended. In an IPv4 scenario, the subscriber typically receives a single public IP address and uses network address translation on the CPE device to provide connectivity to other devices in the local area network. However, one of the primary motivations behind the development of IPv6 was to eliminate the need for network address translation. Consequently, the broadband network gateway must assign additional IPv6 addresses to the subscriber's devices. This process is known as IPv6 prefix delegation and is done via the DHCPv6 protocol. The Broadband Forums TR-187 document, which outlines IPv6 deployment in broadband networks, suggests that service providers delegate an IPv6 prefix of /56 to the customer. This allows the customer to create up to 256 subnets within their network. Okay, let's switch to our RBFS system and go through the configuration step by step. First, we activate IPv6CP as a network control protocol. In addition, we enable the router advertisement protocol for address management on the WAN link and DHCPv6 for prefix delegation. Next, we enable the IPv6 address family. Similar to IPv4, we configure an IPv6 pool name. As an additional configuration step, we add the prefix delegation pool name. The pool name configuration is optional and can be skipped if IPv6 address allocation is handled by Radius. We also specify a primary and secondary DNS server. Finally, we need to define the IPv6 address pools, one for the WAN addresses with prefix /64 and another one for the delegated prefix with /56. In order to demonstrate that this dual stack configuration is working as expected, we start the BNG Blaster once more, this time, with a dual stack IPv4 IPv6 configuration and generate 5 sessions. As we can see, 5 sessions are successfully established. To summarize, in contrast to IPv4, with IPv6 we need 2 address pools, one for the WAN links and one for the delegated prefix. In addition to activating the IPv6 address family and IPv6 CP, enabling router advertisement protocol and DHCPv6 is also necessary. To conclude the section on configuring PPPoE and RBFS, we would like to briefly mention that there are also service profiles. The service profiles are attached to the access interface similar to the access profile. Without going into further details, the service profiles offer the possibility of providing subscriber-specific services, such as quality of service, multicast support, or network address translation. Now that we have successfully configured PPPoE and have also seen that subscribers have logged on to the system, we would like to introduce some commands that are helpful for monitoring and troubleshooting subscriber sessions. A BNG can easily terminate thousands or even tens of thousands subscriber sessions. Therefore, a simple show command is not very helpful if you are looking for a specific subscriber. RBFS offers the option of specifying a filter on the CLI that searches for sessions with predefined criteria, for example interface name, VLANs, MAC address, or username. Let's demonstrate this by filtering on inner VLAN 103. Each subscriber in RBFS is uniquely identified by a 64-bit number called the subscriber ID, which remains unique across all RBFS processes and even across chassis in the context of high availability. Once we have the subscriber's session ID, we can retrieve more information about the session using the detail keyword. For instance, the username and the subscriber's IFL are displayed, which consists of the physical port combined with the session ID. We can also extract the IPv4 and IPv6 information related to this session. We are already familiar with the show subscriber history command. Again, we can use filters to restrict the output. As these are PPPoE sessions, we can also use the show PPPoE session command to list all subscribers. This command also supports filter options to restrict the output. In combination with the session ID and detail keyword, we can obtain useful information about the PPP, LCP and IPCP status of the session. To get a quick overview, we can use the show PPPoE discovery packets and show PPPoE discovery errors commands. If local IP address pools are configured, we can monitor them with the show subscriber pool command. The summary option provides a list of all configured IP address pools as well as their usage. It is also possible to view the allocation of IP addresses from a specific pool. I have put together the commands that I just showed you into a couple of slides as a reference. The most important takeaway is that we have the show PPPoE session and show subscriber command hierarchies, which display slightly different information, the former focusing more on PPP session-related information and the latter focusing on Layer 3 information. Both commands use the same session IDs and share the ability to filter the output based on customer information. Please pause the video if you need more time to review them. If you have multiple BNGs, configuring user-specific options on each device does not scale, as it can lead to inconsistencies, especially when migrating users from one BNG to another. The next section discusses Radius, a method that simplifies operations by providing user-centric configuration and data in a central repository. Remote Authentication Dial-in User Service, short Radius, is a networking protocol that provides centralized authentication, authorization, and accounting, or AAA, for users who connect and use a network service. Authentication is the process of validating subscriber identities before allowing them access to the network. Authorization determines what kind of services a user is allowed to use. Accounting tracks user activities, such as the number of packets and bytes transmitted, and the amount of time the session is active. This information can be used for billing purposes. Radius is a client-server protocol. The Radius server is responsible for validating user credentials. Subscribers are connected to a BNG device, which serves as a Radius client. In Radius terminology, the BNG is called a Network Access Server. Radius uses UDP for communication. Let's dive into the protocol details. When a PPPoE client initiates a PPP session, it sends a PAP or CHAP authentication request to the BNG, including the username and password. Instead of using a local user database, the BNG sends a Radius access request to the Radius server. The access request contains the user's credentials, along with an authenticator ID and the NAS IP address. The Radius server responds with either an access reject or access accept message. The access accept message may contain additional configuration options, such as framed IP address, framed route, DNS server, etc. The BNG sends a PAP or CHAP authentication acknowledged to the PPPoE client once it receives the access accept from the Radius server. If Radius accounting is enabled, the BNG sends an accounting request of type accounting start to the Radius server, including the username and accounting data. The Radius server replies with an accounting response packet. When a PPPoE session ends, either due to timeout or user disconnect, the BNG sends an accounting request of type accounting stop to the Radius server, which is acknowledged by an accounting response packet. The accounting stop message contains total data usage in both directions, the number of packets as well as the volume, and the session duration. Since a BNG might crash or the accounting stop message might be lost, Radius provides interim accounting updates, which the BNG can send periodically to avoid the loss of accounting data. Change of authorization is a mechanism that allows dynamic changes to a subscriber's session without needing to tear down and re-establish the session. For instance, a Radius server can send a change of authorization request to the BNG to adjust session parameters like bandwidth changes or activation or deactivation of legal interception. The BNG responds to the change of authorization request with either an acknowledge to accept the changes, or a negative acknowledge message to reject the changes. Now, let's get through the Radius configuration on RBFS step by step. We have seen this diagram in parts before, and we already know that an AAA profile is a mandatory part of the configuration. When configuring Radius, there are two additional building blocks. The first is the Radius server. You can configure multiple Radius servers. The Radius server configuration includes the IP address of the server, the credentials for communication, and whether this server can be used for authentication, accounting, or both. Optionally, you can define the UDP port for authentication and accounting communication. The Radius profile defines which of the previously defined servers should be used for authentication and accounting. Although a particular Radius server might be capable of handling both authentication and accounting, in the Radius profile, you specify that it should only perform one of these tasks. You can provide a list of servers to allow for redundancy or load balancing. Finally, the Radius profile is linked to the AAA profile. Before we do the Radius configuration itself, we must ensure that the Radius servers are reachable in our network. In most cases, the Radius servers are located in a data center and the communication is done in-band via the core network. For sake of simplicity, our Radius server is directly connected to interface hostif 000. Next, we define a radius server using the set access radius server command hierarchy. The radius server is simply named SN, but you can choose any name. We define the routing instance, the IP address of the server, the source IP address from which we are sending our packets, and the passkey for the radius communication. Afterwards, we enable authentication and accounting and also define the corresponding UDP ports. The radius profile is configured using the set access radius profile command. I use the name myRadius, but again, you can choose any name you like. We define the NAS identifier to be BNG and the NAS IP address. Both of these values might be used by the radius server to take specific decisions. We also configure the NAS port type to be Ethernet. Finally, we add our radius server to the list authentication and accounting servers. Our previously defined AAA profile did not use any authentication. So, let's first delete the old profile and create a new one using authentication order and accounting order both set to radius. We then link our radius profile to this AAA profile. Let's switch to the BNG Blaster again and generate a couple of PPPoE subscriber sessions. On our BNG system, we can verify that 5 PPPoE sessions were successfully set up. We can use the show radius server command to list all radius servers including their status. If we add the server name to this command, we get a packet statistic and we can confirm that radius packets were sent and received. How can we verify that these sessions were really authenticated by radius? If we check the IP address pool allocation, we can see that 4 addresses were allocated from each pool. However, we have 5 sessions established. The pool allocation reveals that one of the subscribers did not get an IP address assigned from the pool. Inspecting this subscriber in detail, we see that it got an IP address, which is not part of the pool. The reason is that this IP address was provided by the radius server as part of the framed IP address attribute, which proves that the radius server did accept this user. Once again, I have created an overview slide summarizing all the CLI commands related to radius configuration that I have just demonstrated. I hope you enjoyed this clip on configuring PPPoE subscriber management in RBFS. Thanks for your attention.